All right, good evening and welcome to lecture number 11 for MT225. Tonight, we're not introducing any new content. We're just having some open time for review and to set us up for our exam next Wednesday. So a week from tonight, most of us will be at the hangar and taking the starting into the exam. I plan on being there at about 4:30, and I will be bringing some food in, so bear that in mind. So don't rush out if you are, unless you absolutely have to, I suppose. Otherwise, you run the risk of missing out on some pizza. So I'll be there 4:30 also for any questions, last minute or otherwise, that you have regarding the exam. So tonight we're just going to open up for any questions you might have. I anticipate there's at least one question on the homework, and then if you don't have anything specific, I've got some sample problems prepared for you to work on, and we'll do it as basically one big practicum session. So homework 4 is due today, and I will open up the floor for questions on that in a moment. Quiz 3, I returned the results on that yesterday. For the most part, doing pretty well. Common errors ended up being significant figures. Again, you got to pay attention to the sig fig information. In this one, it was phrased a little bit differently. It said to round to the appropriate number of sig figs, and when we talked about how to determine the appropriate number of sig figs, that was based on what the input information is. You use the minimum precision of the input information, and the minimum precision we had there was 4. So we had to round to 4 sig figs for our final answers. Let's see. So quiz 3 was returned. We will have quiz 4 next Monday, same setup. So quiz 4 is on non-concurrent force systems, the content for homework 4. And so there will be a problem posted sometime Sunday afternoon. And homework 5 has also been posted to the website. Now, homework 5 is due a week from today, but it is something that will not cause you a penalty if you choose not to do it. It is something that is worth taking a look at. It's all on distributed forces, so it's based in the content we went over on Monday night, and it can only help you to prepare for the exam. So it's a couple more sample problems you can work on prior to the exam. And if you turn it in and you do better on it than you have on at least one of your past or future official homework assignments, I'll substitute the grade. So that's how it's a bonus. It'll never hurt you to turn it in, and it won't harm you to not turn it in. So keep that in mind as you look at that and continue consider your preparations for the exam next Wednesday. I did post a sample exam 1. I mentioned that on Monday, and that is up there on the website. That's the exam and solutions from last spring. So gives you a sense of the kind of problems you can expect and what the format's going to look like. So that should hopefully alleviate any test anxiety you might have. All right. So anyone have any questions on the homework?
Could you go over number 5?
Which one was that?
Number 5.
Number 5. Yep. So let's take a look at that. Number 5 is the one I expected there to be some questions on. It looks a little different, but it's something if you have got a pretty solid grasp of the principles, you'll be able to figure it out. And sometimes all that takes is just breaking it down once and seeing how to apply the equations of equilibrium in this setup. So let's go over to the assignment first, and we'll take a look at that. So number 5 was this problem here. So here we have what looks close to a simply supported beam, and I suppose it would still be considered a simply supported beam in that it has a pinned support and a roller support. The kind of odd thing about it is the roller is sitting on an inclined plane. Now, the first thing you'd have to do in looking at a problem like this is decide, is this even physical? Does this make sense? Could this be an equilibrium situation? And easy way to think about it would be like if you've done manual labor or anything like that in the past, if you've ever moved anything around with a wheelbarrow or went up a ramp with a wheelbarrow, imagine stopping on that ramp and holding the wheelbarrow by the handles and keeping everything in equilibrium. That's essentially the situation that you've got here. The pinned support is you holding on to the handles of the wheelbarrow, and you have to apply some force up to hold the thing from falling down, but you also have to be pushing forward, or else it's going to want to roll back down the hill. The wheel would be the roller. So it is a physical situation. We just have to know how to figure it out in the analysis. And if you draw your free body diagram and handle your unknown forces correctly, or at least how to handle the setup, the equations fall right out. So it's not too bad. So let's draw the free body diagram. So in the free body diagram here, I'm just going to sketch this before I take it off the display. So we've got our beam. I just want to get the applied forces in the geometry down. So we have 800 pounds of force pushing down and to the left at an angle to horizontal of 60 degrees. And that was 3 feet from the support. Then we had 5 feet to a 500-pound load. And then 3 feet to the other support. So overall, 11-foot beam. Great. Prime number for our length of our beam. That always makes for nice numbers. So there's the free body or there's at least part of the free body diagram. The part I haven't included yet are the supports. Now the pin support should be pretty old habit by now of just replacing that with 2 perpendicular forces. I'm going to call those RAX and RAY. The support at B should have been the point that was a little bit harder to figure out. And the key piece of information to know is that rollers apply a force perpendicular to whatever surface they're on. So if we've got a horizontal surface, the roller is going to apply a force perpendicular to that. So it would apply a vertical force. If we've got a tilted surface, then the reaction from that support is going to be perpendicular to that surface. It's going to be off of vertical by the same amount as the incline is off of horizontal. So if we kind of sketch that out over here, our roller on this 30-degree angle is going to apply a force perpendicular to that surface. And so it's going to be 30 degrees off of vertical. So our reaction force here is something we don't know. We don't know the value of it, but we do know the angle it's at, just like we would as if this was sitting on a flat surface. We'd know that it's vertical, and that we'd only have to worry about the magnitude. The reason we have 2 forces here is a pinned support contributes 2 unknowns. A pinned support, we don't know what force it's applying or what direction in total it's applying when you add up RAX and RAY. Rollers, we always know the direction. We know the direction because it's always perpendicular to whatever surface it's on. So I've got my reaction at B, which I'll label over here, RB. I can't really call it RBX or RBY because I don't have it all in the X or all in the Y direction. But I do know something about it. I know its direction. And I know it's going to be 30 degrees off of vertical. So there's our free body diagram, and we'll see how we can work that out here in a moment. Does the free body diagram make sense so far? The sticking point's usually about how to represent this reaction force, but once you lock into that key fact that the roller applies a force perpendicular to the surface that it sits on, that usually is enough to resolve the issue. So let's see how we'd solve it. So we've got all our forces here. We have to do our equations of equilibrium by taking our sum of forces in the x and y direction and sum of moments about a point. So let's define a coordinate system here. We'll call x to the right and y up positive and counterclockwise moments negative, or positive, excuse me. Do our sum of forces in the x direction. So sum of forces in the x direction, I've got RAX to the right, at least that's what I've assumed, so I'm going to put it in as positive. I'm going to have a piece of this 800-pound force. This 800-pound force is really two forces, a horizontal and a vertical force. I've got my adjacent and my opposite side, so I'm going to have a horizontal force and a vertical force. I drew that horizontal just a little long, but you get the picture. Those can be resolved into components. The adjacent side is x, and adjacent goes with cosine. So I'm going to have 800 cosine of 60 degrees to the left, so it's negative. I don't have any x direction contribution from the 500-pound force, but I will have a piece of RB. If I knew a number for RB, I'd be just looking for this opposite side. That opposite side would be my x component of RB. It's opposite the 30-degree angle, so it's opposite goes with cosine, so or goes with sine, excuse me. So it's sine of 30 degrees. So the magnitude here is RB sine 30. So I have RB sine 30. That's the piece of RB that is pushing to the left. And since it is pushing to the left, we put that in as negative. So we have RB sine of 30 degrees. So that's our sum of forces in the x direction. Nothing else has an x component, just three vectors, so three terms. Then we've got our sum of forces in the y direction. In the y direction, we've got RAY, that's positive because it's pointed up, at least that's what I've assumed. I'm going to have a piece of the 800-pound force. I'm going to have that vertical piece. Well, that's opposite the 60-degree angle, so that is opposite goes with sine. So we have 800 sine 60. And that's pointed down, so it's negative. We have a negative 500 pounds. And then we have the adjacent piece of RB. RB's adjacent piece should be like that somewhere. RB's adjacent piece, adjacent goes with cosine, so RB cosine of 30. And that's up, so it's positive. So those are our sums of forces in the x and y direction, and unfortunately, neither of those right now can be solved because we don't have enough information. We have two unknowns in the x direction sum. When we set that equal to 0 to make our equation of equilibrium, we can't solve it because we are missing two unknowns, RAX and RB. Same with the y direction equation. When we set that equal to 0, we're missing two pieces. So this is why we need our moment equation. Our moment equation will give us the missing piece if we pick our pivot point correctly. As long as we pick our pivot point at one of the unknowns, at one of the supports, then we'll end up with equations we can solve, and we'll avoid having to do simultaneous equations. Now, where you pick your pivot point, As long as it's at one of the supports, it really doesn't make any difference. You might be inclined to go with your habit of picking A if that's what you've done all along. That's going to make the moment a little complex because you're going to have to over here realize that only the perpendicular component is going to contribute to the moment. The parallel component, this side, this piece right here, is not going to have a moment. If that makes you uncomfortable, one way to do it would be to pick B as your pivot point. Then it doesn't matter what RB does. If you're not sure about how you've represented it, pick your pivot point there. You'll knock out RB and you won't have to worry about it. Then you'll get an answer for RAY. Out of that, you can solve RB from the Y direction equation. Either way works. And since we habitually go to the left-hand side here, why don't we go to the right this time? So I'm going to pick B as my pivot point, just to do things a little bit differently. So I'm going to take my sum of moments about point B. So my sum of moments about point B, I'm going to try to keep it all on the display here. So we have to look at what's going to have a moment. Well, everything about the reaction force at B is out. Doesn't matter whether it's horizontal or vertical, it's pushing on the pivot point. So it doesn't have a moment. The 500-pound force, that'll have a moment since it's got an arm away from point B. Some of this 800-pound force is going to have a moment. The vertical piece here will have a moment. So the horizontal piece won't, since that's along the pivot point. It's going to run through the pivot point if this beam is really thin. But the vertical piece will have a moment. RAX, its line of action goes through the pivot point, so it's out. But RAY has an arm. RAY has an arm of 11 feet. So it's definitely going to have a moment. So we've got 1, 2, 3 forces. 3 forces that have moments, that will generate moments, as they say, around point B. So let's get them into the equation here. We've got RAY pushing up 11 feet away. So arm is 11 feet and the force is RAY. If we pin here at B and push up at A, that'll give us a clockwise rotation, and clockwise rotations are negative. The vertical piece of this 800-pound force, that was the opposite side. So that's 800 sine 60. Now, I haven't calculated what 800 sine 60 is just yet, but we'll figure that out in a second. That's the amount of force that's creating a moment. I still need an arm for that. Remember, force moment is arm times force. So perpendicular force times arm. There's the perpendicular force, 800 sine 60. The arm is 8 feet. So I'll have an 8 in here. We'll work that out. So we have 8 times 800 sine 60. That's our moment. If we're pinned here and pushing down there, that's going to be a counterclockwise rotation. So counterclockwise is positive. So it goes into the sum positive. And then we've got the 500-pound force. That 500-pound force is 3 feet away. 3 times 500 is 1,500. So we have a 1,500 foot-pound force there. Pinned at B, pushing down there, that's going to be a counterclockwise rotation. So that's positive. So there we go. Those are the only terms that have moments, only forces that have moments, and that sum is equal to 0. So now the rest of it's just crunching the numbers. If you've got the equations set up right, you're basically 90% done. The rest of it's just getting things into your calculator and getting the numbers out. Be careful with that, by the way. I have been detecting a number of calculation errors. People have the right numbers on their pages, but what they calculate with those numbers isn't what my calculator says when I calculate it out. So something strange is happening there. So be careful. Check those numbers out. Be really careful with your calculator. Sometimes I can figure out what people did, and I try a little bit too, but sometimes no idea what you might have fat fingered in there if you hit multiple keys or something like that. So let's run the numbers down here, but these are our equations. Let's work with the moment equation since that's the only one we've got that we can solve. Can't really do anything to simplify the 11 RAY, the negative 11 RAY. If we go to the calculator on 8 times 800 sine of 60, we have 5,552.56. And according to our problem, they really didn't tell us how many sig figs to use. So I'm going to arbitrarily say I want 3 sig figs in my final answer. So I'm going to keep 5 in my calculations. So this will be 5,542.6 plus 1,500 equals 0. 5542.6 plus 1,500. So cleaned up a little bit, our equation becomes negative 11 RAY plus 7,042.6 equals 0. And if we add 11 RAY to both sides, we'll have 7,042.6 equals 11 RAY. Divide both sides by 11, and we'll get RAY equals 640.24. And that's pounds. So 640 plus another quarter pound, roughly. That's how hard you'd have to be lifting up on the end of that wheelbarrow to keep it supported. So 640.24 pounds. It came out positive, so we know our assumed direction of up is correct. So that's our value for RAY. Still to 5 sig figs because we've got to plug it in to our y direction equation. So let's go ahead and do that. RAY was 640.24 pounds.
Hey, Tom.
Yeah, go ahead.
So we can get a negative answer as long as our arrow is pointing down in the free body diagram, right?
Yeah, if you drew your free body diagram and the arrow was pointing down, that was your assumption that when you drew your free body diagram, you didn't really know what RAY was doing. So if you assumed it was down, then you got a negative answer. And your negative answer tells you your assumption is wrong. A negative answer does not necessarily tell you it's down. It's telling you whatever you drew was wrong. And you've got to flip that direction at the end of the problem. So it's the math telling you you made a bad assumption and you should have gone the other way on it.
Okay, it makes sense.
That makes sense. So I know it's sometimes a little bit hard because math classes kind of teach you, well, if it comes out negative, it's to the left. And if it comes out positive, it's to the right. Well, that's a little bit away from how we can actually use the tools. That's nice in a math world where everything is perfect and all your assumptions come out right the first time. But in reality, sometimes we have to make a guess, and sometimes those guesses are wrong. And having a negative answer just tells us we guessed the wrong way. So 640.24 pounds. So let's go back up to the y direction equation. 800 sine 60, we can calculate that out. That's 692.82 pounds minus 500 plus RB cosine 30. I'm going to leave that as cosine 30 for just a second. And that equals 0. If we run the numbers we have down, we've got 640.24, we've got 692.82. We're subtracting that, and we're subtracting 500. So we have a negative 552.58 plus RB cosine 30 degrees equals 0. So to write this in our typical equation form, we'd add 552.58 to both sides. So that would be RB cosine 30 equals 552.58. So that's our equation and what we have to solve. And the reason I'm leaving it written this way is because this comes up all the time in working with truss problems, where you're going to end up with your coefficient essentially being a trig function. And I like to leave the trig functions written as cosine or sine until I'm ready to actually use those numbers, because I find there's a much higher rate of making mistakes. If people get some weird decimal number and then write that a couple of times, it's really easy to lose a digit or transpose a couple digits. It's a lot harder to screw up writing cosine of 30. To get my final answer, I would have to divide this out. So I'd divide both sides by whatever the value of cosine of 30 is. That would cancel out the cosine 30s, and I'd just have RB. Now I can go to my calculator, and I don't run the risk of punching in numbers wrong or fat fingering things when I key in the value of cosine 30. I just let the calculator do it. So I can do 552.58 and divide it by the cosine of 30. Now, cosine of 30 is not that bad of a number, but it's still something that that you might mistakenly miswrite. Especially things with double digits, they always throw me off. I always have to be very careful with that, because I have a tendency, if I have 0.8660, to write 0.8860 and double up the wrong digit. So the more you can keep in your calculator, the less you have to transcribe, and the better your chances are of getting the correct answer. So I'm just going to divide by the value my calculator spit out for the cosine of 30 right in the calculator, and that comes out to be 638.01 pounds. And that came out positive, meaning we had our direction right, which we didn't really have any guesswork on that direction. So it's pretty reasonable that it came out positive. So there's our value for RB. Now just one value we need is RAX. We needed RB to get that. So we've got RAX minus 800 cosine of 60, and cosine of 60 is a nicer number. That's 1/2, so minus 400, minus RB, which is 638.01 times the sine of 30. And here, since I'm not dividing by it or manipulating or anything like that, here I can go ahead and get the value, because this is just a number now. 638.01 times the sine of 30. Well, the sine of 30 is still a nice number for the most part. 0.5, 638.01 times that, 319.01. So we have times 0.5 there. So we have RAX minus 400 minus 319.01 equals 0. Combining the numbers together and solving that, we should get that RAX is 719.01. Also positive, which, if you think of the physical example of this, rolling something up a hill, this is going to be trying to roll back down. So unless you're pushing to the right, you have nothing opposing that force trying to take things back down the hill. And don't forget our units, that's pounds. So there we've got our answers. Almost to the final answer. We haven't phrased everything to the right number of sig figs just yet. In this case, I said at the beginning of the problem for this, and if you solve this using a different number of sig figs or didn't round off in the end and left it as 5 sig figs, that's fine. The problem was not specific on it, so I can't hold you to much. I would hold you to not being unreasonable about it and rounding things down to 1 or 2 sig figs, but if it's not specified, then you have to use your own judgment to figure out what to keep. And generally 5 sig figs will do the job for you. 5 sig figs rounding off in between in the middle of the problem and 3 in the end is generally a good rule of thumb to follow if no other information is available. So let's present our final answers. So I've got RAX rounded to 3 sig figs, that's just 719 pounds. RAY was 640.24. Now my first pass at trying to round that would be to write it as 640. But 640 looks like 2 sig figs because trailing zeros don't count unless there's a decimal point there. So I could put a decimal there. That would be one way to solve the problem. That's a special notation when dealing with sig figs to tell you that everything up to that decimal point is significant, that there are no placeholder zeros. It just happened to come out 0 as a result of the calculation. If that is something that makes you uncomfortable writing that, or you don't think you'd remember that, just remember when it looks hard to put it in to get the right number of sig figs, write it in scientific notation. 6.40 times 10 to the second pounds will clearly communicate that you're dealing with 3 sig figs. And then we had RB at 638 pounds. So there we go. Any questions there?
You got to put all arrows next to those too?
You can. I mean, it's as long as you've got your free body diagram there that has those values there. It's a little hard to do for RB because it's off at a weird angle. If you really weren't sure about how to write it with just putting arrows next to it, you could redraw your free body diagram with the numbers on them. That would work too. But if I have positive values here, I'm going to look at your free body diagram for your definitions of your directions. So anything that communicates the correct direction. But yeah, it wouldn't be a problem at all to go down here and say, well, RAX was 719 pounds up, RAY to the right, and this was off at a 30-degree angle. Gets a little awkward on that last one to kind of write things out, but anything that properly communicates the direction, whether it's referencing back to your free body diagram or doing a little sketch, laying the answers out on a new free body diagram, anything works as long as it's clear.
All right.
Any other questions on this one? All right. So let's see here. So that takes care of our homework questions. There we are. So today we're just working on practice problems, practice equilibrium problems specifically, but if there are other areas that you are having issues with or that you would prefer to review, I'll give you a chance to let me know about that. One of the things I suggested prior to this class was to take a look at the sample exam. Does anyone have any specific questions off of the sample exam that we're giving them difficulty or that they'd like to see gone over? All right. Now, for the most part, if we summarize the content that we've been through the last several weeks since the beginning of the semester, basically roughly 5 weeks or so of real content, and we started out with mathematical preliminaries, algebra, solving equations, all that. And to this point, pretty much every problem you've solved is involved solving equations. We've had a couple problems where we've needed to do some simultaneous equations. And I might I'll probably throw as our second example, our second sample problem, one of those, as that's about the hardest that could possibly come up. We had simultaneous equations. We worked with vectors and adding vectors together. Finding resultants using inverse tangent and the Pythagorean theorem to go from components to magnitude and direction. we used sine and cosine. Now you've used sine and cosine a lot more since then to get components. We haven't spent a lot of time going back, though. In some of the equilibrium problems, we had that practice, and that'll be up in our first problem tonight. But the majority of our real effort here has been in the last couple of weeks looking at non-concurrent and concurrent force problems. The problems from last week and the problems from this week. Those are the bulk of the application and the skills that we set up in the first couple weeks of the class. So the first problem tonight that I will set up just like a practicum problem here. So I'm going to set it up, and you can I'll pause the video and you'll take a few minutes to set it up and get a solution going. If you run into any problems along the way, speak up and I'll try to help you out with it. And then after a few minutes, we'll go over the solution. So let's start with a box on a wire problem, but box on a wire problem that is looking a little bit different. Instead of having the wire supported on the ceiling, let's have the wire supported on the walls. So we've got a couple walls here, and we'll hang our box like this. And let's make that a 2,000-pound box. And in the wire to the right, let's see, we'll have an angle here of 35 degrees. And let's see. We'll make this have a 1,400-pound tension on it. And what we want to find out is what's the tension in the other rope and what angle is that going to make with the wall. So find the tension and the angle to 3 sig figs. All right, so that's our first problem, and we'll pause for time on that. All right, so let's take a look. So we've got my proposed answers in red here, but like I mentioned last time, I do this really quickly to get the answers. I might make some errors here and there, so if something doesn't look right, don't 100% discount that my values might be wrong. So let's go ahead and start with our free body diagram. And as in all the box on a wire kind of problems, our free body diagram is really the free body diagram of that intersection point. This is a concurrent force problem. And in concurrent force problems, there's always one point where all the forces intersect. That makes a natural selection as our body because all the forces are easy to represent there. So we've got this point that is the body in equilibrium. It's being pulled down with a 2,000-pound force. It's being pulled up and to the right with 1,400 pounds of force. And we have to figure out where to put this angle. And this is where a little bit of high school geometry comes in. When you have two parallel lines and you have a slanted line going through them, the angles in the corners, if you think of this as kind of a sideways Z, like that, the corner angles have the same values. they had a big long thing that, at least when I was in high school, they made us say that when two parallel lines are cut by a transversal, then the interior angles are congruent. Opposite interior angles are congruent. That's just a fancy way of saying that the corners of the Z have the same angle. So that can be useful in moving angles around. So a common error would be to try to write that 35 degrees as an angle down here, but it's an angle to vertical. So we have a 35-degree angle there. On the other side, we don't have that kind of problem because we don't know exactly what the angle is, but we can still use that same idea of the parallel lines and the line across. That angle's also got to be theta. So when we draw it in our free body diagram, we've got our angle T and we've got this angle theta to vertical. So none of the angles are referenced to horizontal. So there we've got our free body diagram. This is a concurrent force system, so there's no moment because none of the forces have an arm about that point. So why not pick that as our pivot point? And we get a really unenlightening moment equation that just says 0 equals 0. So the moment equation doesn't bias anything here. We just have forces in the x and the y direction. Now the big trick to these, and the one that tends to give people problems with these types of problems, the thing they forget is that when you know nothing about the force, you don't know magnitude, you don't know direction, just represent the components. Use Tx and Ty, or Fx and Fy, or whatever you choose to call them. That's going to be better than using T cosine theta and T sine theta. If you ever have two unknowns multiplied together, and T and theta are two of our two unknowns in this problem, when you have those multiplied together, it makes it much more difficult to solve the problem. So it's not impossible, but it requires more algebraic sophistication than I really care to bring in. It's a lot easier just to change the variables and treat the two unknowns as the coordinates, as the components. And then we'll use Pythagorean theorem and inverse tangent to get our angle and our magnitude. So let's do our sum of forces. So our sum of forces in the x direction. And now I'm going to be assuming that we're feeling comfortable enough at this point with trig that we can just kind of jump into the components and I don't have to label them out, vector 1, vector 2, vector 3, and the x and the y components. Certainly if that helps you and it helps you keep things organized, absolutely do it. But I think the majority of the class is getting comfortable enough with trig to be able to just read the components off and then calculate them out. So here, fx, sum of forces in the x direction, we've got tx to the left, so that'll be a negative tx. We've got a piece of the 1,400 pounds to the right, and that piece would be the opposite piece. That'd be the horizontal piece there, so opposite goes with sine, so we'd have 1,400 sine of 35 degrees, and we'll figure out what number that is here in a moment. That is to the right, so it's positive. So that's our sum in the x direction. Nothing else has an x direction component. We'll take our sums in the y direction. We've got a positive ty. We've got a piece of that 1,400 pounds, and that's the vertical piece. That's the adjacent piece, and adjacent goes with cosine. And a good clue that you're going to be using cosine is you use sine in the other equation. If you use sine in one, you're going to use cosine in the other. So 1,400 cosine 35, and that's up, so it's positive. And then we've got minus 2,000. So that's our sum in the y direction. Now, since this point is in equilibrium, these sums must equal 0. So the x direction equation we can solve right away if we crunch the numbers down a little bit. 1,400 sine of 35 That's 803.01. So we have minus tx plus 803.01 equals 0. And the solution of that one's not too hard. And I'll leave that to you to bring it the rest of the way and make sure that it comes out positive. 803.01 pounds. So it came out positive because we assumed correctly. We had no choice but to assume correctly. It would have, there was only one physical direction this could be in and have this be in equilibrium. So 803.01 pounds. For the y direction equation, we need, we'd need our 1400 cosine of 35 minus 2000. That comes out negative 853.19. That equals 0. And again, I'll leave the full details of the solution to you, but ty equals 853.19 pounds. So those are our components, tx and ty. They both came out positive. We got our directions right. We had no choice but to get the directions right. There was only one set of directions that would work. But now we need our magnitude and direction. We still have to satisfy the objectives of the problem, which was to find t and theta. So the easiest thing to do here is to redraw this a little bit. And since I want this angle down here in the corner, I'm going to draw ty, then tx to get to t. So ty, tx, that's my tension and my angle. Now ty was 853.19 pounds, and tx was 803.01 pounds. The angle is going to be given by inverse tangent of opposite over adjacent. So my angle is going to be the inverse tangent of opposite over adjacent. So 803.01 over 853.19. And that gives me 803.01. And that's right, 853.19. Inverse tangent, 43.265 degrees, which when rounded to 3 sig figs gives us 43.3. The tension is going to be given by the Pythagorean theorem. We have the opposite and the adjacent side, so we'd have 803.01 squared plus 853.19 squared, and take the square root of that whole thing. So 803.01 squared, 853.19 squared, add them, square root, and that's where we get our tension of 1171.6 pounds. So 1171.6 pounds rounded to 3 sig figs. If we count up to our third sig fig, 1, 2, 3, we're going to round there. First digit we're throwing away is a 1, so we just get rid of it, but we can't turn this into 117. We got to put a placeholder 0 there. So 117 with a 0, 1,070 pounds. We definitely don't want to put a decimal point there since that would imply 4 sig figs. This, as it sits, has 3. So our answer's up here. We're good. Or at least I made the same mistake twice and got the same answers. So it looks good there. Any questions on that one? All right, let's try a little more challenging one. Same setup, but this time we have the angles, but we don't have the forces. So I'll stick with the same kind of box on a wire problem. And we'll make the box, let's say, 200 pounds this time. We'll make that a 45-degree angle. And we'll make this one a 30-degree angle. And we want to find out the tensions, T1 and T2, that put this system into equilibrium. So take a few minutes, get that one set up, see if we can come up with a solution for that one. And we'll be back in a few minutes to work through the solution. All right, so let's take a look at this one. Now, this probably is about the most complex kind of problem you could get involving the most sophisticated mathematics up to this point. So, in fact, it's probably about the most sophisticated math you'd have to deal with in this program or in this class at all. So if you can handle this problem, chances are you'd be good at pretty much any other problem once you can get down to the equations. The rest of it's just skill in getting your free body diagram and building those equations correctly. But once you got the equations, you can solve them. If you can set them up right and you can handle the math, you'd be able to solve it. So let's draw our free body diagram. So again, we're drawing the free body diagram of that point. So we'll do that over here. We've got 200 pounds down. Up and to the right, we've got T2, and that's at a 45-degree angle, again, to vertical. And then we've got T1 over here, 30 degrees. Define our coordinate system: to the right, positive x, and up, positive y. So there's our free body diagram. And we'll go ahead and get our sums. So we have our sum of forces in the x direction. We're going to have a piece of T1 to the left. We're going to have the opposite piece. So opposite goes with sine. So that would be T1 sine of 30 degrees. It's to the left, so it's negative. We'll have a piece of T2 to the right, so that'll be positive T2. It's also going to be the opposite piece. So the opposite piece is going to go with sine. So we have sine of 45 degrees. And that's all that has x components. Then we'll have our sum of forces in the y direction. In the y direction, we've got the vertical piece of T1 up, so positive T1 cosine 30, that's the adjacent side. We'll have the vertical piece of T2, which is the adjacent side, cosine of 45. So plus T2 cosine 45. Then we've got the 200 pounds pulling down, minus 200. Since we're in equilibrium, the sums equal 0. So unfortunately, we've ended up with a set of simultaneous equations, which is what happens when you have only two unknowns and you are missing both the magnitudes of those unknowns, but you know the angles. When we have everything missing from one, like we did in the previous problem, those tend to be able to be solved without dealing with simultaneous equations. But here they're all mixed together. So we're going to have to set up our simultaneous equations. So let's clean the equations up a little bit. Sine of 30 is 0.5, so we'll have negative 0.5 T1 from our x direction equation's first term. Sine of 45 is 0.70711. So that's our new x direction equation, negative 0.5 t1 plus 0.70711 t2 equals 0. And if we do the same for the second equation, the first thing I do is add the 200 to both sides, so I'll end up with 200 over there. And then it's t1 cosine of 30, that's 0.86603 t1 plus 0.70711 t2 equals 0. So definitely simultaneous equations. So we're going to have to figure out how to unwrap this. And the way we can do that is to look for that built-in sign difference. If there is a sign difference there, then we can use that to our advantage. And it looks like T1 has that. Now, T2 might be attractive too. And in fact, if you are feeling comfortable with simultaneous equations, you might have jumped to just dealing with T2 since they already have the same coefficient. But that just happens to be a fluke of the fact that this is 45 degrees. If it wasn't 45 degrees, you wouldn't have that same coefficient, and you'd need to be able to figure out a different way around it. So I'm going to not use that. I'm going to assume that I'm going to work the problem as if those two came out different. So I'm not going to use any special advantages of having used 45 degrees here. So the way that I've demonstrated this in the past is the way I'm going to do this one now. We can modify these equations by using division. We want to turn the coefficients of the variable we've targeted for elimination into positive and negative 1. That way, when we add the two equations together, they'll cancel out. I'm going to preserve the negative up here in the x equation so that I can add that to the positive and eliminate those unknowns. So the first equation, I'm going to divide through by 0.5. If I divide every term by the same number, I'll get a new looking equation, but it has the same content as the old equation. So if I divide the first term by 0.5, I get negative t1. If I divide the second term by 0.5, I get 1.4142 t2. And if I divide 0 by 0.5, I just get 0. Now here I'm rounding to 5 sig figs since I want 3 good sig figs in the end. So that's my new x equation, cleaned up a little bit. The y equation, I'm going to divide by 0.86603. So I'll divide the first term by 0.86603. That'll give me a positive t1. The second term, when I divide 0.70711 by 0.86603, I get 0.81650. That'll be T2 equals 200 divided by 0.86603. You got to divide every single term on both sides by the same number. Otherwise, you'll break the equation and you'll get meaningless answers. And when I divide 200 by 0.86603, I get 230.94. So there we've got two equations that are ready for elimination. When I add these two equations together, the T1s will cancel. Negative T1 plus a positive T1 is 0. That'll leave me with just T2 and just a number, and that I can solve. So when I add the coefficients together here for T2, I end up with something I didn't write down. So I'll have to go back to my calculator on that one. We had 1.4142 and 0.81650. That gives us 2.2307 T2. Pretty ugly coefficient, but we can deal with that. It'll go away soon. 230.94. Solve it the same as if we had a whole number out in front. We always just divide by whatever that coefficient is. And if we do that, we get T2 equals 103.53. and that would be pounds. So T2, 103.53 pounds. Now we're not done yet. We've got half the answer. We need the other half. We need T1. And we can go back to either of the two equations to do that. I think the x direction equation is a little simpler here. So I'm going to plug this back into the x direction equation. I'll write that down over here. I've got negative 0.5 T1 plus 0.70711 times the value of T2, and T2 is 103.53. That equals 0. So we can solve that. 0.70711 times 103.53 gives us 73.207. So we have negative 0.5 T1 plus 73.207 equals 0. And if we solve the resulting equation here, we could add negative 0.5 T1 to both sides, divide by 0.5, and we'll end up with T1 equals 146.41. So 146.41 for T1 and 103.53 for T2. Let's go back and look at the original problem here and make sure those numbers make some sort of sense. The more vertical a rope is, the more of this load it's going to be supporting. The more horizontal it is, the more it's just really pulling against the other rope. So if we look at our values here, T1 came out to be a little bit came out steeper here, or came out to be a bigger value. T2 came out to be the smaller value. So the 30-degree angle, the drawing's a little bit misleading. 30-degree angle to vertical is a steeper angle. It's closer to 0. 45 is dead in the middle. So it's it's between steep and shallow. So the 30-degree line, T1, is supporting more of the load. For our final answers, we round to 3 sig figs, and that's pretty straightforward from these, 146 and 104. Any questions on this one? All right, we're just at about we're a little past our break time here, so we're going to pause for a 10-minute break. When we come back from break, I've got 3 non-concurrent problems to take a look at. Since they're a little more recent in memory and that we've just done a homework assignment on those, there's not really anything too complex to throw in. I've got one little challenge problem that we'll do kind of at the end, but the problems we'll do in the practicum session will involve, at least one will involve a distributed force. So that's the subject of our current homework assignment, the one that's due next week. So if you want a little review on that, stick around and we'll work on those problems. So we'll pause here for about 10 minutes. All right, so here's our first practicum problem of the evening. We've got a distributed force problem. We've got a uniformly distributed force across the entire length of this beam. And then also we've got a concentrated force applied at the same time. And I want to make sure you can see that on my display. It's right under the recording logo. So there we go. 3 kilonewtons applied at the very end of the beam, and then a distributed load across the entire length of 900 kilonewtons per meter. And we want to find out in this sort of cantilevered beam what the reactions are at A and B. So take a few minutes and set that up and solve it. And we'll be back with a solution in a few minutes. Just a correction for those following along at home. The distributed force is 900 newtons per meter, not 900 kilonewtons per meter. All right, so let's take a look at the solution here. So the first step is to draw our free body diagram. But before that, we've got to figure out what our equivalent concentrated force is going to look like for this distributed force. So here we've got this distributed force, uniformly distributed force, 900 newtons per meter, spread out over 10 meters. So last time we saw to find the equivalent point force magnitude, we had to multiply the height of the rectangle by the width of the rectangle. So this is 10 meters wide and 900 newtons per meter high. That's 9,000 newtons or 9 kilonewtons. And because it's a uniformly distributed force, that equivalent 9 kilonewtons is going to be right in the middle of the beam, 5 meters in from either end. So now that we've got that, we can go to our free body diagram. So in the free body diagram, we've got our beam. Right in the middle, we'll have 9 kilonewtons. At the end, the left end, we have 3 kilonewtons. Then 4 meters in from the end, we've got our pin support, which I shouldn't have drawn there. Got RAY and RAX, the forces the pinned support supplies. And then at the far end of the beam, the right end of the beam, we've got our vertical RBY. And so we've got distance here of 6 meters, distance here of 4 meters, and this distance is 1 meter. So there we've got our geometry, and we can go ahead and set up our equations. So you might look at this one ahead of time, just kind of try to figure things out. And I strongly encourage you to do that, to take a look at it, see if you can get some idea of how things are going to look. Well, we've got no sideways forces here. We've got no X direction forces. So that means that our pin support isn't going to have to react in that direction. So we're going to anticipate RAX is 0 here, since there's no applied load to react to in that direction. But then we've got this kind of strange behavior here of the 9 kilonewtons sitting in the middle, and then 3 kilonewtons on each edge or on each side. Well, the issue there is that is this going to balance one way or another? Is it going to try to pivot to the right side or left side? Is this RBY going to have to push up or pull down to balance the beam? Well, that's a question that we might not be able to answer, because we don't have a good we don't really have a way other than solving the equations to kind of estimate how much torque each one of those is going to supply. Because we've got a bigger force here, but it's closer in to this pin support. We've got a smaller force out here, but it's farther away. Maybe those effects will cancel out. So it's a little too close to call. So I've made a guess here that my reaction at B is going to have to push up, and the math will tell me whether that guess was good. So let's set up our equation. Sum of forces in the X direction, we've got RAX and nothing else. So RAX equals 0. In the Y direction, we've got -3 kilonewtons. We've got -9 kilonewtons. And we've got positive RAY and positive RBY. And that equals 0. And then we've got our moments about a point. Now, the point you choose should be a point that is at one of your supports. Don't make the mistake of trying to pick the left end of the beam. Because if you pick the left end of the beam, you're going to end up with two unknowns in your moment equation. You'll actually end up with a set of simultaneous equations you'll have to solve. And that's not any fun. So you could either pick point A or point B. I picked point A here just because it was a little bit different than picking something at the end of a beam. So if you pick point A, we've got some moments here. RAY and RAX will not produce a moment. RBY will, because it's got an arm, and the 9 kilonewtons has an arm, so it will create a moment there. And then we have the 3 kilonewton force. So that will create a moment. So we've got three terms in our moment equation about point A. So working left to right here, we've got 3 kilonewtons 4 meters away. That's 12 kilonewton meters. If we're pinning at A and pushing down over here, that would be a counterclockwise moment. And counterclockwise moments are positive. So that goes into the sum positive. We've got 9 kilonewtons 1 meter away. So that would be 9 kilonewton meters. But if we're pinned at A and we push down here, that would be a clockwise moment. And clockwise moments are negative. And then we've got RBY, which is 6 meters away. So we have 6 RBY. If we're pinning at A and pushing up at B, that would be a counterclockwise moment, and counterclockwise moments are positive. So that sum equals 0. And that equation we can solve. 12 minus 9 is a positive 3, so we have 3 plus 6 RBY equals 0. Subtracting 3 from both sides, we get 6 RBY equals negative 3. Divide both sides by 6, and RBY is negative 0.5 kilonewtons. So negative half a kilonewton. The negative tells us our assumption was wrong. So this 3 kilonewton force is far enough away to have enough moment to cause this thing to rotate, to try to rotate it counterclockwise. So the support at B really has to hold down instead of push up. So negative 0.5 kilonewtons. We can go back here to, we're stuck with our assumptions until we're done with the equation. So we have to use that negative in RBY. So we'll replace RBY with negative 0.5. So we have negative 3 plus negative 9 plus negative 0.5. That's negative 12.5. So we have negative 12.5 RAY. Negative 12.5 plus RAY equals 0. So RAY must be negative 12.5 or positive 12.5. So add negative 12.5 to both sides. And RAY is 12.5 kilonewtons. Now here we actually have exact answers. We haven't rounded anything. So it's we have to formally meet the objectives of the problem, which says to write your answers to 4 sig figs. So when we write our final answers up, we'd do 12.50 to get 4 sig figs there, and I would keep it as 0.5000 kilonewtons, because writing 500, you could do 500.0, I suppose, but either way works. And then that one's down. So there we go. There's the answer on that one. Any questions there? All right, so let's try another one here. This one, we will have a little bit of different setup anyway, but it's, again, one of these things that looks a little different, but you can still apply your same principles to it. Let's say we've got a wall. And on that wall, there is a pinned support. We have some beam out here where we have a rope attached to a ceiling and some load applied here. So let's make this a 50-pound load. We'll have the distance between the rope and the end of the beam be 2 feet. And we'll go 4 feet here. So the question is going to say, what are the reactions? Find the reactions at A and the tension in the rope. And we'll do 3 sig figs on this one. So there we go. There's the problem. Looks a little bit different, but look at it a little bit first. See if you buy if it's in equilibrium. See how the structure is going to actually handle the loads, or try to get a feel for that. And then once you decide you believe it's in equilibrium, then draw your free body diagram and work out your equations. All right, so let's take a look at this one. Now, it's always good to make sure when you start a problem that you can actually solve it. And by that, I mean that you aren't missing too many pieces. We always have to make sure there's correspondence between the number of equations that we have and the number of unknowns that we've got. Now, in this problem, we've got 3 unknowns. We have 2 unknowns from our pin support. That's why we always write RAX and RAY, or RBX and RBY. It's 2 reactions there. T, the tension, is just giving us 1 unknown because the direction is given. The direction's vertical. So we've got 3 unknowns. We're going to have 3 equations. We can solve the problem. If we counted that up and we had 4 unknowns, we'd be in trouble. If we have 4 unknowns and only 3 equations, it means we're not going to be able to come up with a complete solution. We might get some numbers out. We could run the equations, and if we're lucky, we'll get 2 numbers out of it. But the 3rd equation we're not going to be able to solve. And that means we need to go get more information elsewhere. And we'll be seeing that in the coming weeks. We're getting to a few problems where we end up dealing with that. So let's set up our free body diagram. So the free body diagram is going to be of the beam. So we'll have our beam set up there. At the end, we've got 50 pounds pulling down. 2 feet in from that, we've got our tension. And then at the very end of the beam, we've got RAX and RAY. We've got our reactions. And because it's kind of an oddball problem, something I maybe don't have the best physical intuition with, I'm just going to use my default RAX to the right and RAY up and let the math tell me if those work. So we've got 4 feet here and 2 feet there. So there's the free body diagram. Don't forget the coordinate system. There we go. So let's do our sum of forces in the x direction. So sum of forces in the x direction, we've just got RAX to the right and nothing else. There are no sideways forces in this. Even though we're supporting off of a wall instead of the floor, there are still no side loads. So there's no loads in the x direction, so there's nothing to react against. So RAX is 0. Sum of forces in the y direction, we've got a positive RAY, we've got a positive T, and then we've got a negative 50 pounds. So that says the same thing all of our y directions equations have said. Whatever's pushing up has got to equal what's pulling down. So when we set that equal to 0, what we're really saying is RAY plus the tension has to equal 50 pounds. And then we've got our sum of moments about a point, and the natural point to pick here would be A. That'll knock out RAX and RAY, but both the tension and the 50-pound force will have a moment. The tension's 4 feet away, so we have 4T. And the direction of T is up here, so if we're pinned at A and pushing up or pulling up at T, that would be a counterclockwise moment, so that's positive. And then we've got 50 pounds, 6 feet away. Don't mistakenly use that 2 feet unless you picked the pivot point at T, at where the rope is attached. So it's 6 feet away, 50 pounds, so that's 300 foot-pounds. Pinned at A, pulling down at the end of the beam would cause a clockwise rotation, so that's negative. So we have 4T minus 300, and we can solve that pretty readily. And it's a pretty simple equation, so I'll leave that to you to solve, but the tension should come out to be a positive 75 pounds, which I've written here to 3 sig fig, 75.0 pounds. We can substitute that back into the y direction equation. We get RAY plus 75 minus 50 equals 0. That'll give us RAY plus 25 equals 0, which means RAY must be negative 25 pounds. So RAY is negative 25 pounds. So my assumption here was wrong. I thought it had to push up, but it has to pull down. And it makes sense if you think about it. If you think about this being suspended from the rope, if you push down on one end of the beam, the other beam's going to want to rise. If this support were to break, this thing's going to move up. So our support has to pull down to hold this in equilibrium. So 25 pounds down. Any questions on that one? All right, so last problem of the night, we're going to keep the same setup of this problem, but I'm going to change one thing. I'm going to put that rope at an angle. So let's redraw the problem. And if we redraw the problem that way, we have our wall and our pinned support. We've got our beam. Put 50 pounds at the end. We'll have the same geometry, same attachment point, but now we'll have the rope connected up at an angle. So we have a tension. And we've got support point A there, same distances, 4 feet and 2 feet. Now, unlike the first problem that we worked on this evening, where we had an unknown tension and an unknown angle, I'd be in trouble here if I didn't give you an angle, because we'd have too many unknowns. If I didn't know the angle and the tension in the rope, that would be 2 unknowns. I also have 2 unknowns from my pin. That's 4 unknowns. I've only got 3 equations. So I've got to give you an angle here. So let's make that angle 40 degrees. So we'll find out what the tension in the rope would be and what the support reaction forces at A would be if we've got that rope at 40 degrees. So same question, find the reactions at A. And the tension T to 3 sig figs. All right, so let's take a look. So the equation should have looked pretty similar the difference here is some trig's going to come in because now we're holding this tension off to an angle. There's the vertical piece of that. It's what's got to do the job that the vertical rope did in the previous problem. So one way to look at this is to think, well, the vertical piece of this force, the tension now has to be high enough so that the vertical piece is providing the force that the previous rope did. So it's got to be 75 pounds pulling up. So being at a 40-degree angle, to get 75 pounds pulling up, you're going to need a higher tension. It's kind of like on an airplane when we go into a bank, and the lift is now tilted off at an angle. That same lift doesn't support the airplane anymore. We have to increase the lift to get to stay at a level attitude or level altitude. So let's draw the free body diagram. So we've got our beam. We have our 50-pound force there. We have our tension at our 40-degree angle. And RAY and RAX. Now, the other effect of pulling this rope off to one side or another is now we're creating a sideways force. So now there's something that the pin support is going to have to react to in the X direction. So those are the two major consequences. It doesn't change anything about how the vertical part of the problem works. So we should expect the same outcome with RAY that we did in the previous one. The reaction at A doesn't, in the Y direction, really doesn't care what this rope is doing as long as it's pulling up hard enough. A moment. Let's try that again. There we go. So let's do our sum of forces in the X direction. We have RAX to the right, but now we have a piece of that tension to the left. We have the adjacent piece. So that would be cosine, T cosine 40 degrees. We have our sum of forces in the Y direction. We have a positive RAY. We have the vertical piece of our tension. That's the opposite side. So that's going to be T sine 40. And then we have 50 pounds down. And then for our moment equation, still pick point A, because it'll knock out RAX and RAY. We just got to be careful about that tension. Only the vertical component of tension is going to create a moment. The horizontal piece will not. So we need T sine 40 as our force. The arm was 4 feet, just like in the last problem. So here, instead of 4T, in the previous problem, I have 4T sine 40, just that vertical piece. And then we have all that 50 pounds, 6 feet away. So that's still the minus 300. So if we put the two equations kind of side to side here, here are the equations with the rope vertically up, RAX and nothing else, RAY plus T minus 50 and 4T minus 300. We've just basically replaced the Y component, which was all just T before. Now it's just T sine 40. So when we solve the moment equation, we'll add 300 to both sides. We have 4T sine 40 equals 300. And we want to divide everything out that isn't T. So we divide both sides by 4 sine 40. That'll cancel out the 4 and the sine 40, leave it just with T. And on the right, I'd have 300 divided by 4 sine 40. So 300 divided by 4 divided by the sine of 40 gives us 116.68. And that is pounds. So 116.68 pounds. Now that we know that, we can go back into the Y and the X equations and solve for those. Well, here we have RAY plus T sine 40. We just divided out the sine 40 here. So when we put it back in, we're going to get back to exactly where we were here. 75 minus 50 equals 0. So this will have exactly the same solution as it did in the previous problem. RAY equals negative 25. And that's how we knew it was 25 pounds down. If we go back up to the x direction equation, we have RAX minus T116.68 cosine 40 and 116.68 cosine of 40. That's 89.382. So RAX, once you solve that all the way out, will be a positive 89.382. That's how much the rope is pulling to the side. So that's how much the support has to push in the opposite direction to balance it out. So rounding off to 3 sig figs per the specification in the problem, 89.4 pounds came out positive, so it matches our assumption to the right. 25 pounds down, 25.0 for RAY. And then to round properly to 3 sig figs, for some reason I glitched and wrote it as 4 sig figs. So thank you for calling me out on that. But to 3 sig figs, 116.68, 117. So 117 pounds. Any questions there? All right. Well, hopefully the review was helpful here tonight. And to go back to the notes here for a moment, next time we will do a little bit of an introduction to trusses, and we'll get a little more finesse with moment and kind of set up the basic problem for the truss. We won't get too far into it, but we'll lay some groundwork that will help us out when we're done with our exam and we're into class week after next. So that's next time, and that's all I've got for you for the evening. Anyone have any questions? All right, well, have a good evening, and I will have a good weekend, and I'll see you Monday.